Here we go. We're good.
Welcome to another live session, and welcome to all the new students. The floor is open for questions on anything from comets to cosmology.
All right, so Jerry writes in an email, the universe is described as smooth on a large scale, but lumpy on a small scale. Stars and galaxies develop in the localized lumpy areas. Could you discuss and add some clarity to this?
It's an important part of cosmology that the universe is smooth, and the question is, what does that mean? One of the foundational principles of cosmology, and it's an assumption, in fact, is called the cosmological principle, and it is that the universe is smooth, is isotropic, and homogeneous. Now, and those words have very particular meaning in science and in physics. Homogeneous is the smooth part. It means that our region of the universe on a suitably large scale is no different than any other region of the universe. Isotropic means that the universe looks the same in every direction. We see the same types of galaxies, the same numbers of galaxies, roughly. So isotropy is easy to check because we can just count galaxies, say, with the Hubble Space Telescope or any deep imaging survey, and we do indeed see the same types of galaxies and roughly the same numbers within statistical counting errors in any direction. That's been tested. And in fact, the microwave background, which is the remnant radiation left over from the Big Bang, is smooth to 1 part in 100,000, or isotropic, which is to say the same temperature in every direction. The true test of homogeneity, though, is difficult to do, because as soon as we look out in space or move to a region that is remote, we're looking at a region that's earlier in time. So distant light is old light, and that means it is difficult to say exactly that our region of the universe is exactly the same as all other regions, because when we look at those other distant regions, we're looking at them as they were rather than as they are. So testing homogeneity is actually difficult in principle because of light travel time, look-back time. However, as much as we can test it, there is no indication that our region of the universe is atypical, which is to say that although we live in a concentration of mass, a galaxy that was formed by gravity and clustering early on, and our galaxy is part of a local group of galaxies, a few dozen strong, and we're on the edge of a Virgo cluster of galaxies, which is maybe a few thousand galaxies and a fairly large overconcentration of matter. That itself is a part of the Virgo supercluster, which is maybe tens of thousands of galaxies spread over a couple of maybe 100 million light years. Those type of structures are seen everywhere else. And what the smoothness really means is if you go on a sufficiently large scale, where that essentially means 300 to 500 million light year chunk of the universe, that 300 to 500 million light year size chunk is essentially the same mean density, the same mean number of galaxies, the same type of structures wherever you go in the universe. And that, in that sense, the universe is smooth. And what that also means, given that gravity formed all the structures on various scales, such as stars, galaxies, clusters, and superclusters, it means that gravity has not had time to form structures on any larger scale than 100 million light years or so. And in fact, we have evidence that things like superclusters are still forming. They haven't fully formed, whereas galaxies clearly had fully formed billions of years ago. So it's quite a long answer to quite a simple question, but it's at the core of cosmology, the smoothness of the universe.
And then Irene has a sort of related question, but it's really a clarification about the microwave background radiation. She doesn't understand why we are still surrounded in every direction by the microwave radiation emitted from the surface of last scattering. Shouldn't these photons have been finite in number and restricted to a specific area of space, like the surface of that sphere?
So it's a good question because it gets to a fundamental issue about the universe, which is, are we at a special location? Is the universe spherical, for example? Does it have a shape? Is it expanding into something or nothing? And the answer to all of those questions is no. It's not any special shape that we can determine. Microwave background radiation actually demonstrates that space is Euclidean, which is to say almost perfectly flat within 1% or so, one of the most precise measurements in cosmology. So the universe, which is to say space-time, has no particular geometric shape. It is flat and smooth, more or less. And And there's no particular privileged location within the universe, because the Hubble expansion we see, the recession of galaxies in every direction, would be seen by any other intelligent creature on a different galaxy, which is to say that we're part of three-dimensional space and the space itself is expanding. And so that's the heart of the answer to the question of the microwaves. You just have to imagine that we are embedded in a three-dimensional expanding space-time situation where that space-time, due to expansion, has been, the radiation within it has been getting cooler as time goes by. And the matter, of course, has been getting less dense because it's diluted over a larger volume. Well, and if you trace that back in time, what you come to is a time about 400,000 years after the origin event, the Big Bang, when the density was sufficient and the temperature was sufficient that the hydrogen was ionized, or rather going in the forward direction to cooler temperatures. The hydrogen for the first time was allowed to become stable. So protons attached to electrons and form neutral hydrogen atoms. And that was happening everywhere in three-dimensional space. It was happening around what would eventually become the Milky Way galaxy, and it was happening at remote locations in this three-dimensional space. So once again, no special position, no sense of a sphere, no sense of an edge, no sense of a preferred geometry. It's a little hard to imagine, but basically there's no imposition of geometry or an external situation on the universe, because none is required in the theory. And so that transition from the gas being at a temperature, the radiation in the universe at a temperature about 3000 Kelvin, corresponded to the photons essentially bouncing around and scattering off electrons freely, and so not traveling freely. And so we were, if we could have been alive 400,000 years or before, after the Big Bang, we would have been literally in a fog, because radiation, which was then the temperature equivalent to red light, was not traveling freely. As the universe expanded and cooled, the hydrogen atoms become stable, the electrons attach to the protons, and the photons, these red photons representing a temperature of 3000 Kelvin, start to travel freely. And so it's that we see in every direction in the sky. But when we say we see the microwave radiation from that era, 400,000 years after the Big Bang, in every direction in the sky, that does not mean we're at the center of anything or there's a privileged position, just as there's no privileged position of the Milky Way within the expanding space-time. So it's a little, it seems like a paradox or a conundrum, but it isn't, because you have to add an external hypothesis to venture that we're expanding into something, or that there's an edge to space, or that the universe has a geometry, spherical or otherwise, and none of the data suggests that. So we just have to imagine that at every other point in the space-time, the same thing would have been observed. Equally, at a remote, distant location in space-time now, occupants of a galaxy looking out in space with microwave telescopes would see exactly the same radiation and exactly the same last scattering surface, as it's called, 400,000 years after the Big Bang, indicating that they were also once in a denser region where light did not travel freely.
Jerry actually has kind of a follow-up question to that as well, and is interested in understanding more about, the universe is flat and follows Euclidean geometry principles and as such is infinite. Could you clarify, explain what you mean by that?
Right. So it's an interesting result from the last decade or so that space is flat. I mean, what it means is that in three-dimensional geometry experiments in space, if we could do them, we would see the laws of Euclid apply. In other words, if we send out two parallel beams of light from the Earth for vast distances or over vast times, those beams of light would not diverge nor converge. They'd stay parallel, which is the definition of Euclidean space in 3 dimensions. That's what we're saying. Now, how do we know that? Well, first of all, it did not have to be the case. So it's an interesting result. And that's because, as you probably know, general relativity embodies and embeds the idea of curved space-time. That's general relativity that tells us how to describe gravitational lensing, black holes, extreme situations of space-time curvature. So general relativity, our theory of gravity, was built essentially to describe space-time that could be curved, and it could be positively or negatively curved, which is to say light traveling through that space could magnify or demagnify. So general relativity is completely comfortable describing and hypothesizing curved space-time, but it's not what we observe. What we observe is the microwave background, and that's our tool. That's our geometric optics experiment carried out over, obviously, a very large distance. So that radiation we see in the surface of the microwave background has traveled over a time of about 13.8 billion years. It's traveled over a distance of about 40 billion light years. And so that radiation has had a chance to respond to the three-dimensional geometry of space, positive, negative, curved, flat, whatever it is. And the nice thing is that the microwave background has a characteristic angular scale of fluctuations. So when you look at those beautiful maps from WMAP and Planck satellites, you see these speckles of temperature are usually color-coded, where red is a little warmer and blue is a little cooler, or sometimes the other way around. And even to the eye, it does look like they're not totally random and all different sizes. It looks like the speckles have a characteristic angular size, and they do. So math and a full analysis of the data shows that there's a characteristic angular scale of about a degree, twice the diameter of the full moon or the sun in the sky, and that's the speckles that you can even see by your eye seem to dominate. What that means is that we have a characteristic scale, angular scale, in the early universe, 400,000 years after the Big Bang, and that radiation, starting at that temperature of 3,000 Kelvin, 13.8 billion years ago, has traveled for a long period of time to be measured now by our microwave telescopes. And so that radiation and its characteristic angular scale has had a chance to be affected by space-time of the whole, essentially the whole observable universe. So it's a very powerful experiment where we can make a model of a cosmological model of curved space-time using general relativity, and we can ask, do we see the speckles as they would be if the universe had a positive curvature, like the surface of a balloon, only in 3 dimensions, or a negative curvature, like the surface of a saddle, only in 3 dimensions, a little harder to visualize in 3 dimensions, or are the speckles essentially unaffected by their enormous passage through space and time, which means space is flat? And what we see, and what was measured very accurately with WMAP, is flat. All of the things I said are possible. Space could be positively or negatively curved. General relativity, happy to describe those. The theory accommodates them, and with gravity you would almost expect that. Instead, the measurement is very clear, very clean, very accurate, showing that space is flat, has no curvature, and is flat to within 1 or 2%. And that becomes an important attribute of the universe. And since the universe was originally highly curved when the gravity was intense and the space-time was much smaller, it leads to a puzzling cosmology, which is why is the space so flat? And it's not a question I'm going to answer right now, because it would send me off on another long explanation, but that's why the inflationary model was proposed to explain the flatness of space that is now exquisitely measured with WMAP.
All right, Brian has a question from a while ago. When we talk of spectroscopy and Doppler shift, is it true that sidereal drift affects observations in the plane of the ecliptic?
Yeah, absolutely. The reference frame of motion affects all Doppler shifts we observe in the sky. So when we're observing the Doppler shift of a star, or maybe measuring an exoplanet tugging on a star, and so it's the star wobbling backwards and forwards, any measurement of a Doppler shift out in the universe, within the galaxy or even distant galaxies, is measured with respect to motion, the motion of the Earth. And the Earth has a motion. So observed over a long enough period of time with accurate spectroscopy, it's easy to see what could be called sidereal drift, which is essentially the slow change in the measured Doppler shift of a remote object caused by the motion of the Earth through space. That motion obviously has one component from the spin of the Earth, but typically the one that's observed when astronomers make measurements over months is the motion of the Earth around the sun. And that's a relatively small motion compared to the speed of galaxies moving around with their Doppler shifts or their recession velocities, but it's easy to measure. And so when astronomers for any experiment are making measurements over a series of months or years, they have to subtract out or understand this sidereal drift, or this sort of motion of the Earth-Sun system. And of course, if you could observe long enough, the Earth-Sun system is doing an orbit around the Milky Way galaxy, but that takes 250 billion years, so you're not about to measure that.
All right, Don's question has to do with right ascension and declination, with the practical and local use of right ascension and declination. I understand their basic definition. How do I use that information to observe an object in my local sky and time? Do I need to change the values to a local altitude and azimuth?
Yes, you do. These are two completely different coordinate systems, and there's no simple answer I can give off the top of my head, because it actually depends on sort of a lookup table based on a series of formulae. And the formulae actually have to take into account the equation of time, which is the Earth in its orbit, the Earth in its non-uniform motion around the sun. So astronomers essentially like to keep sidereal time. They like to keep time by the stars. And the natural reference plane for for astronomers to track positions in the sky and time is right ascension and declination. And so those are coordinates that are relative to the ecliptic, to the projection of the Earth's equator in the sky. That is, the Earth is at least locked as a sort of spinning object with angular momentum, like a top tilted on its side by 23.5 degrees. So astronomers use that reference system, where the declination relates to is sort of the equivalent of altitude in the altitude azimuth coordinate, and then our angle is roughly the equivalent to azimuth, which is the orientation around the horizon. But these require an understanding of the Earth's spinning rate and its motion around the sun. So there's no simple formula, but there's lookup tables for these. And most of the astronomy apps for amateur astronomy just use these formulas to convert from the astronomer's coordinate system, sidereal time, to the observer's coordinate system, depending on your latitude and longitude. So that's the parameter you have to plug into the system.
All right, Jerry would like to know, with your knowledge as an insider, is there anything that has really astounded astronomers about Pluto with the flyby that has totally surprised or astounded us?
Oh yes, the most dramatic thing to learn about Pluto is that this really small, this geologically small world, so small, of course, that it was booted from the table of the planets to become a dwarf planet. Also, it has no particularly large moon. It has a set of small moons. This object should not be geologically active. Essentially, it should be about as dead as Mercury or the moon. And we look at Mercury and the moon and we see objects with no atmosphere. They're large enough to be round, formed round by gravity, as Pluto is, but they have no atmosphere. They have old cratered surfaces, no evidence of resurfacing, of geological activity, of mountain raising, of volcanism, all that kind of stuff. Pluto, in these amazing forms that have been seen, these icy textured surfaces, has some parts of it that are inferred to be as young as 100 million years. And that's known, of course, because the cratering rate is a well-established quantity based on the amount of debris there is in the space between planets. And so objects with no atmospheres to burn up the incoming debris are constantly being peppered by craters. So if you see an uncratered surface, it has to be young. And so this 100 million years is a strikingly small number for a very, very young surface for a part of Pluto. And of course, the Pluto surface is varied. It doesn't have the same textures everywhere. So clearly, resurfacing has been going on. Certain type of geological activity has been occurring. Perhaps some upwelling of frozen ice to water momentarily on the surface has happened, or maybe other forms of liquid. Basically, nobody knows. So it is truly surprising. It was a shock to planetary scientists to find Pluto to have such an interesting surface, not a boring cratered surface, and to have such young surface, because it should not be geologically active. And that's a pretty simple statement, since geological activity for a small world really correlates with mass, because the geological activity is driven by natural radioactive decay in the rock, and that's simply a function of how much mass there is in the rock. So if you don't have enough mass, and you don't have a large moon, a very large moon very nearby to do a little tidal heating, which is another possible heating mechanism, then there's no particular reason Pluto should be geologically active. And at the moment, it stands as a pretty good mystery for people to solve about Pluto. New Horizons, of course, is sped on out of the solar system, so the data it sent us is all we're going to get.
Right, Stanley has a question and asks, can you speak more about the recent announcement of the death of the universe? The articles didn't compare star formation in the more distant galaxies with the nearer ones. If they looked primarily at older galaxies, wouldn't that skew the interpretation?
So I'm pretty sure you're referring to a research result that got press releases in the last week from the GAMA, G-A-M-A is the acronym, survey. It's Galaxy Mass Assembly Survey. I know a number of the researchers working on it. Simon Driver, who works in Australia, was the lead author, and so I got some press activity. It's a very large, a very impressive survey of essentially how galaxies are assembled, because we know galaxies form by mergers and accretion over cosmic time. And the GAMA survey has looked at hundreds of thousands of galaxies, and it's got panchromatic data. So it's imaging from infrared to ultraviolet wavelengths, which is a very refined way of understanding not just the current star formation rate of a particular galaxy, but the history of star formation. So with that data, for such a large number of galaxies, they can very confidently say not just what the range of star formation rates in all these galaxies are, but what they project to be in the future. And some part of their basic result has actually been known for a decade or more, because we've been studying galaxies with large samples since the Sloan survey started, at least. So the fact that we're in the declining part of the stellar activity history of the universe, that's been well known. The peak of star formation activity in the universe happened at about a redshift of 2 or 3, which is 8 or 9 billion years ago, on an age of 13.8. So for the last 2/3 of the age of the universe, the star formation rate on average has been declining, and that's true of the Milky Way too. And the reasons for that are easy to understand. Galaxies are generally autonomous entities, but they also gain mass by accretion, by interaction, by mergers. And as the universe gets larger and less dense, and the gas thins out, there's less gas to fall onto galaxies to fuel more star formation, and there's less opportunity or lower probability that galaxies will merge and sort of resupply star formation that way. So we expect in an expanding universe that star formation will gradually tail off, and that's in fact what we see. They have enough data, however, to refine these calculations and also project them into the future. So they can argue confidently that since we accept that the universe is going to expand forever, that's a fact of the current expansion rate, and dark energy apparently causing an accelerating expansion rate. So whatever is causing the current decline in star formation rate, it's not going to turn around. It's going to be a continuing process forever. And the end point of that progression is fairly also easy to predict, that galaxies will become more and more isolated. Those that could merge will eventually merge, and that's the only mergers that will be possible, none in the future. And there'll be no more gas supply. Within each galaxy, there is a resupply of gas for star formation, because most stars lose some fraction of their mass in the late stages of their lives. The sun will lose about 1/3 of its mass in 5 billion years when it becomes a planetary nebula. And depending on how they die, with a supernova, you can resupply, you can send 80% or 90% of the mass of the star back into the interstellar medium. Our sun will only send 1/3 back. All stars recycle some material, but that process will gradually end as more and more stars die and become stellar remnants, mostly white dwarfs. And so it's very easy to project, and they projected, the gradual wind down of stellar activity, not just star formation of new stars forming, but the existing stars will eventually die. And the last to die will be the lowest mass stars, the red dwarfs, which will die and just fade away, and just fade to black, basically. And the time scale for that fading, which will take place equally within every galaxy in the universe at slightly different rates, but they all face the same endpoint, is several 100 billion years. The stellar models are not quite good enough to put an accurate time on it, but it's probably about 500 billion years. So they were talking about the dying of the universe, which they measure right now with a snapshot in time, and then they project into the future based on all the properties of these very large number of galaxies they measure. So a very nice result.
All right, so there is a student who has been looking at an article titled "A Giant Protogalactic Disk Linked to the Cosmic Web." And apparently within the research paper, it talks about cold accretion flows and unshocked gas. And they're just wondering what that could mean in terms of hydrodynamic simulations moving along, showing gases moving along filaments throughout the universe.
Right. So that's a field, not too far off one of the research fields I've been working on over the years. First of all, just backing up to some definitions, the cosmic web is a term you'll hear quite often in cosmology. It refers to the three-dimensional structure of entities on the largest scales, that is, beyond galaxies, through the intergalactic medium. And we know already that most of the material, now I'm not talking about dark matter now, but just the normal stuff, and the dark matter follows the normal stuff, or rather the other way around. Most of the normal hydrogen and helium of the universe is not in stars. About 80 to 90% of it is in very diffuse gas. Some of that gas is actually very hot. It's 100,000 Kelvin or more in the intergalactic medium. And some of it is fairly cold when it condenses. So the cosmic web is essentially the three-dimensional architecture of the universe, not traced necessarily by galaxies and stars, but by the diffuse, sometimes hot, sometimes cold hydrogen and helium, primordial material of the universe. And in astronomy, in observation, it's hard to just see the cosmic web. We only sample it in very indirect ways, sometimes using quasars as probes and looking for absorption lines. That's how my research does it. But in a simulation, again, hydrodynamic, which means you take into account the dynamics of the gas and how it's flowing and the fact that it might get heated by shocks or not. Hydrodynamic simulations reveal, if we trust the simulations, which we mostly do, this beautiful cosmic web. And so if you type cosmic web into Google and looked at images, you'd be mostly seeing images from simulations just color-coded with density, so red or blue on black, showing this beautiful egg drop soup type texture, filamentary, three-dimensional complex texture. That's the cosmic web. Now to the question, one issue becomes, since galaxies are still forming stars, how does and beyond actual mergers, which are fairly rare, true mergers of equal-sized galaxies don't happen that much now in the present universe, but many galaxies still have substantial star formation rates, including our galaxy. And one of the little puzzles in cosmology has been, how can galaxies in this sort of old, recent universe sustain the star formation rates they have? Because if you do the math and you look at the reservoir of gas they have, like in the disk of the galaxy, they only have enough gas to sustain their currently observed star formation rates for 1 billion years or less. But they seem to have been doing it for more than 1 billion years. So there's a very simple disconnect there that's been known for some decade or so, and it implies that they're obviously getting a supply of gas another way, not from major mergers, which we can see, and we know the rate of that is quite low, but they have to sustain their currently observed star formation rate with some new supply. And the mechanism that was hypothesized and can be visualized very well in these simulations is what's called cold accretion flow. Generally, if you let gas drop onto a galaxy in gravitational free fall, it will accelerate and compress to the point where it gets shocked and becomes very hot and ionized and so on, and it will glow in X-rays or ultraviolet or something like that. And we would see that. So if gas was falling into galaxies just by gravitational free fall in a spherical or quasi-spherical situation, then we would see a lot of X-ray and UV radiation we simply don't see around galaxies. We see that sometimes in clusters, but not single galaxies. So the hypothesis spurred by the simulations because it's seen in them, is that there must be a cold mode of galaxies getting their gas, and it's called cold mode accretion, and it typically will happen along these filaments that sort of form the cosmic web, where galaxies are at the interstices between the threads and the filaments. The filaments are not purely one-dimensional. Sometimes they're sheet-like and sort of almost two-dimensional. And observing that phenomenon, and then the sidebar on why that happens to be cold, is that in these filaments, the velocity dispersion, or the range of velocities, is actually quite low. It's only a few tens of kilometers per second. And the gas is mostly flowing smoothly, so it actually doesn't get shock heated, so it stays relatively cold. And that means it's hard to observe with an optical or even a radio telescope. And so that's why this cold mode of accretion could have remained invisible to typical observational astronomy, while simulations, putting in the right astrophysics and gravity, seem to see it and predict that it should be happening. And depending on who you talk to and which simulation you look at, the cold mode of accretion in the late universe for a galaxy like the Milky Way could or should be as important or 2 times more important than all other modes of mass onto the galaxy, either by hot gas shock heated, or by mergers, or by eating the small dwarf galaxies, or the other ways galaxies can get gas. So this cold mode accretion along the cosmic web seems to be quite an important phenomenon of why galaxies form stars at the rate they do.
Our next question is about exoplanets. We keep seeing new planet discoveries that say Earth's twin, but then they end up being mostly larger than our planet by quite a bit. How close does a planet have to be to our own for it to be really similar, like in gravity and that kind of thing?
Right. So, there's a fair amount of hype in this field now, because there are 3,000 or more confirmed exoplanets, or over 5,000 candidates, mostly from Kepler. So it's a huge number, and obviously the attention, continues to focus on which is the most Earth-like. And there's a competitive aspect to this. There are a number of groups working on this, and they all want to claim the most Earth-like planet. There are many Earth-like planets in these Kepler catalogs. There are close to 1,000. It is still true that the typical planet, the simple majority of planets found to this point, are like Neptune and Uranus. They're not Jupiter-sized, but they're sort of substantially larger than the Earth, and they're probably gas giants, small gas giants. But even though that's the simple majority, there are close to 1,000, 700 or 800, that are within a factor. And since they're measured by Kepler, we talk about size rather than mass, because Kepler only measures size, not mass. Doppler effect measures mass, and we don't have Doppler effect for most of these. There are 700 or 800 that are within a factor of 3 of the Earth, and that includes factor of 3 smaller. Kepler is quite able to and has found planets smaller than the Earth, which is very exciting. So Earth is no longer the limit, and that's a large number. That's of order 700 or 800 that are Earth-like within a factor of 2 or 3, and within that catalog, there are a few dozen that are really very close to the Earth. Now the data has errors attached, so we don't know the parameters of these planets accurately enough to say this one's within a few percent of the Earth, total twin. The best you can say is within 10 or 20%. But like I said, there are a few dozen that fit that bill. So we have indeed found planets that, as accurate as the data is, are as like Earth-sized as possible. The Doppler method finds Earth mass planets. It's really hard to find Earth mass. The closest the Doppler method has come is of 1.9 times more massive than the Earth. That happened about 3 years ago. And it's got a couple that are roughly twice Earth mass. The Doppler method is also finding pretty close to Earth mass, but not as close as Kepler. The problem is, well, none of those few dozen are in the habitable zone. So we have not yet hit the sweet spot of Earth size or mass and in the habitable zone relative to a sun-like star. That would be an Earth clone. That's what people would mean by an Earth clone, because it would be almost certain that such a planet could have an atmosphere and could have water on its surface. Again, none of that is measured by this data, but it's a good hypothesis. So we're getting close, but no true Earth clone has been found. And so this set of few dozen objects where the size is very close to Earth size are obviously the subject of a lot of work, and we still don't know enough about them.
All right, the Perseid meteor shower happened this week, and I read that the stuff that hits our atmosphere is like the size of a grain of sand. How does it make such a huge meteor streak?
Yeah, it was kind of a bust. My wife and I were out there at 1:30 or 2 in the morning. We just got up, and it's Arizona, so it was really nice. Very pleasant out there at that time in the morning. And I'm not really in a super dark place near the foothills, but it was dark enough. And really the rate was kind of disappointing. It was like one every couple of minutes. So Perseids they can be dust, and it's very hard to predict because the debris strewn out along the comet orbit, which is what the Earth's trajectory intersects, is so variable in density that it varies a lot from year to year. But indeed, as the question suggests, the particles that are causing these little flashes in the sky, sometimes crossing a significant angle across the sky and lasting a few seconds, are tiny. They're sand grain, typically sand grain sized. So most of the debris that's strewn out along a comet trail, or most of the debris that hits the Earth's atmosphere, just in general, you don't have to be in a meteor shower to see these shooting stars, as people call them, which has got nothing to do with what they are, because they're not stars. They're the opposite end of the size spectrum, just same grains of sand or maybe pebble size. So they are arriving at typical velocities of tens of thousands of miles per hour. 10 to 40,000 miles an hour is a pretty good sense of the range. So to see, and what you are seeing is the rapid disintegration, evaporation, burning up of that very small object pretty high in the atmosphere, typically 60 to 80,000 feet up. They don't even make it down. They certainly don't mostly make it to the surface, and most of them don't even make it down to the layer of atmosphere where the weather is. They're pretty high up there. But if you do the math of a small object that might be a gram or less with a velocity of 10,000 miles per hour or 50,000 miles an hour, and it's half mv squared, so it goes as the square of the velocity. That huge velocity gives them phenomenal kinetic energy. And so when that kinetic energy is essentially converted very quickly into heat as they go from vacuum of space to upper atmosphere, that is enough to fry, evaporate, light up the little rock, the tiny pebble, the dust grain, and make it glow pretty brightly. So you're converting, even in a tiny object, a huge amount, really, relatively speaking, a large amount of kinetic energy into heat and radiant energy or light very quickly. And that's the meteor shower, or the individual event.
All right, Irene asks, regarding type 1a supernova, there has been recent information that they don't all emit the same light over the same time periods. If so, what would that mean about dark energy and cosmology?
So we've got to unpack this a little, because type 1a supernovae are the type of supernova that occurs in a binary system, where there's a star, essentially one star in a tight orbiting binary, is spooning mass, or just through the sort of gravitational interaction, mass is falling onto the less massive star until it tilts over the Chandrasekhar limit and it detonates as a supernova. And the astrophysics is such that because the supernova is sort of very well regulated, because the star that explodes is just having mass spooned onto it, sort of like thinking of taking some uranium and gradually adding uranium to it until it's critical mass, and then at that point it's explosive. So the same thing with these stars. They're very well regulated because of the way the mass is being steadily added, and so when they blow up, they appear to blow up at a very constant rate. So the absolute amount of energy, the number of watts or number of ergs per second at their peak brightness, is the same from one supernova type, one type 1a supernova, to another within 15%. So that's a result from 15 or 20 years ago. And it was that quality, that character of having a constant luminosity, that lets them be used as distance indicators. And it was their use as distance indicators that was allowed astronomers in 1995 to impute the accelerating universe and discover dark energy. So since dark energy's discovery depended on the properties of type 1a supernovae, and still 20 years later, that was the only direct evidence for something that we want to call dark energy, it's pretty important that we understand type 1a supernovae. And we do think we do, because I sort of described the mechanism by which they explode, and it's pretty well understood. We've modeled it in supercomputers. But in detail, the observations of type 1a supernovae show they're not all the same. They have chemical differences, so the gas and the chemical composition of the gas is different from one to another, and that affects the way they explode and the luminosity of their explosion. Just to the observational astronomer who follows type 1a supernovae, their light curve, or sort of the time between when they're rising to peak brightness and then falling to fade away forever again, that time varies. It varies in a way that correlates with luminosity, and that's not completely understood. We can measure it and we can calibrate that relationship and use it as part of the distance indicator measurement, but that makes people a little uncomfortable that we don't fully understand all the astrophysics. And so the result that Irene's referring to is people working pretty hard on the details of type 1a supernovae just because they want to understand them in their own right. There are people who don't care about dark energy, who just study supernovae and want to understand them. But we absolutely need to understand them very well to use them as dark energy probes or diagnostics. And the data that's coming out as people study these larger samples and find more nuances in their behavior is a little puzzling, and it's a little disturbing because it shows that the relationships that people use to infer dark energy in 1995 are not as simple as we thought. It's not to the level where they're wrong, where what people did in the mid-90s to say dark energy is there where the universe is accelerating is not wrong. It's not like this deconstructs it or debunks it at all. But it's showing some effects that are quite significant in terms of how you measure the dark energy and in how much dark energy you infer from your measurement of the supernovae. And the jury is essentially out on what the full implication of these results are. But it's an important piece of work, definitely.
All right, David has kind of a general question about your thoughts on the Big Bounce theory versus or in conjunction with the Big Bang, especially since the first fraction of the second of the Big Bang theory is murky.
So the Big Bounce idea, was commonly, I think it was first proposed in the 1950s when the Big Bang was out there as an idea but hadn't been affirmed through the microwave background radiation discovery, which is 1964. And it was the idea that in an expanding universe, there are clearly a couple of possible outcomes, depending on the amount of mass and the gravity of all the objects in the universe act to decelerate the expansion. In principle, if there was sufficient mass, you could either stop the expansion asymptotically, taking forever to do so, and that was called a critical density universe, sort of coasting to a maximum three-dimensional size, taking an infinite time to do so. Sort of transitional case, if you like, between an open universe that it just expands forever at a slower and slower rate, and one that expands forever at a slower and slower rate heading towards a maximum size. And then on the other side of that, a universe that did indeed reach a maximum three-dimensional size, and then because of the gravity of all the matter in the universe starts to recollapse again towards doing a time reversal of the chronology from the Big Bang back towards what was called a big crunch. So those three possibilities were all on the table in the 1950s and 60s. By the 1970s and 80s, it became clear that even with dark matter on the table, it was starting to be mapped out in the 1970s, there wasn't enough mass in the universe, normal and dark, to overcome the expansion rate. So the universe should have been decelerating, but not sufficiently to overcome the expansion. In the 90s, with the discovery of dark energy and the acceleration, that became even more emphatic. And so with dark energy accelerating the expansion, it became, to astronomers, to cosmologists, beyond doubt that the universe would simply expand forever. So at that point, the Big bounce or the big crunch and then possible other bouncing universes into the infinite future was sort of taken off the table completely because it's just not observationally indicated. However, actually, it was taken off the table theoretically in the 1970s because Stephen Hawking, one of the less well-known pieces of work he did, was he was working on the entropy of the universe, the amount of disorder. And it turns out that the universe has an unusually low entropy. And that's an interesting statement. How do we know that everything there is has a low entropy, and relative to what? It's sort of relative to all the possible situations that could arise from a fiery origin. You know, the Big Bang, this sort of chaotic situation of extremely high temperature, energy, and density, is an intrinsically disordered situation, has high entropy. And so to have an outcome, to live in a universe that's now old and cold and has relatively low entropy is sort of needs a little explanation. So Hawking took that notion, that observed fact that the universe has relatively low entropy, and noted that in the scenario where there's a big crunch and then a re-expansion, so a bounce, and then a bouncing universe, if you like, that has a big bang, a big crunch, then another big bang, and so on, he sort of worked through the math of that as well as he could with relativity. And he argued that the entropy of the universe should increase, the disorder should increase through the big bounce, the big crunch and the bounce, and then another big bang. So, I mean, it was pushing gravity theory to its limit to do the calculation, but he claimed the result. And therefore, it becomes very difficult to explain why, since that could be an endless process, and it always tends towards higher entropy, why does the universe have low entropy now? So he used that almost on logical grounds to argue that we were extremely unlikely to live in a bouncing universe, because a bouncing universe at some arbitrary time would have very high entropy, much higher than we observe. So we just don't look like we're in a universe that is the aftermath of a series of big bangs and big crunches. So that was interesting, that even before the observation that the universe is essentially unlikely to recollapse, the theorists had decided that that scenario was not viable.
All right, and Jerry asks, I believe your department is using special hardware to speed up simulations. Could you briefly describe the hardware and where I can find details?
Sure. There's two aspects to this, and this is not my field, so I'm going to not be giving gory details because I simply don't know them. But the astrophysical simulations have migrated from supercomputers. They were done for most of the early time of simulations, which is the 70s and 80s and 90s, on supercomputers. Most of the people I know who did simulations had to go to the national labs, Lawrence Livermore, Los Alamos, where the biggest computers and most powerful computers in the world were, mostly working on nuclear weapons research, and they got parts of the time on those computers to do their simulations. Well, Moore's law and the sort of phenomenal power of the desktop has now taken simulations onto the desktop. And the two types of innovation, the large-scale architectural innovation, involves just putting together a multiprocessor machine. So you're essentially using the same kind of fast, by fast we're talking, for the clock speed on a typical decent PC now is 2 or 3 gigahertz. If you go to the high end of that, it's 5 or 6 gigahertz. Those are pretty expensive processors. So you don't even have to go to the very high end, but you take pretty fast processors and you just essentially create a cluster of them. You create a grid of them. And so, and this is called a Beowulf cluster, the particular geometry. So if you want to look this up on the web, you'll see a lot of information about Beowulf clusters. That's just the name of that's a proprietary brand, but it's done with all sorts of processors. So you're using a PC architecture, but you're parallelizing the code, and you're using a lot of individually fast and together used in parallel super fast processors. And the number could be 32, 64, it's usually some factor of 2 for computational reasons. So a Beowulf cluster, could have the power of 30, 60, 100 PCs. So it's just pretty impressive and getting close to supercomputer power. That's one manner of increasing computational power in a small platform, a PC-type platform. The other happens at the level of the hardware itself, at the level of the motherboard or the processors themselves. So another way to go, and these are not mutually exclusive, sometimes both happen together, is not to just buy standard off-the-shelf processors and run them in parallel and parallelize your code that's doing the calculation. Another way is to customize the hardware itself. And so there's a whole little industry, and it's now spilled into other work like client predicting weather and other things where you need a lot of computer power, or doing three-dimensional models of protein folding, so the biologists and geneticists are using these computers for their difficult calculations. This work involves customizing the boards themselves, and so you're actually changing the architecture of the motherboard, of the processors themselves, the chips themselves, and how they process information. And essentially you're hardwiring into the motherboard some of the algorithms that you would use, or the manner of calculation you would use to do gravity simulation or hydrodynamic simulation. And I think it's again an acronym, GRAPE, the GRAPE boards, GRAPE, that's an acronym, it's got nothing to do with the fruit. GRAPE boards are the ones that we use here, and we have Beowulf clusters running and so on. And there's this whole, like I said, this little niche industry in Silicon Valley of producing these customized boards to do these very powerful calculations. And if their customers were only astronomers, they wouldn't probably make these boards, but actually they have quite a lot of customers in other fields that need huge parallelized and customized computation, customized at the level of the microprocessor itself.
And that's our last question for today. Thank you very much for everybody.
Great set of questions, computations to cosmology. So we'll be back again in a couple of weeks. Thank you.